Hey everyone, we're going to continue with chapter 3 today. We're going to break chapter 3 into two parts. Today we're going to talk about linear relationships, and we're going to start by talking about identifying areas of increase, decrease, or no change. So when we're looking at a graph, we want to make sure that we can identify places where the graph increases. For example, from A to B, we see increase. From C to D, we see increase. But from B to C, we don't see increase, and we actually don't see decrease, so we would call that an area of no change from B to C right here. When we have an increase in our graph, we think that that is a positive slope. As x increases, y increases. As our independent variable increases, our dependent variable decreases. When we have areas of decrease, we think of that as a negative slope. And we don't see that on this first graph here. So let's look at our second graph, Marie's trip to work. From A to B, her distance from home is increasing. We see that as time increases, her distance increases. So that's positive. From B to C, we know that her distance is decreasing, and that's negative. She's returning back to home, according to the graph. Then from C to D, she's moving away. From D to E, she's not going anywhere. Time is increasing, but distance is not. So although we're moving in this way, we are not moving vertically. All right, let's continue on. So slope-intercept form we use to represent the relationship between x and y when we have a linear situation. So what we just saw on the previous page is a linear situation, and when we have a slope, that's going to be known also as our rate of change. Rate of change. And our y-intercept tells us that when x is 0, y is equal to this number b. On our graph, that would look like x is 1, x is 2, x is 3. Well, if x were 0, that's on the y-axis. So anything on the y-axis, any of these points, doesn't matter what the number is going to have an x value of 0. Okay? So identifying functions. So inputs should always have reliable outputs. If you give an input of a number, there should always be one output. You can rely on that output always being the same, which means that we cannot have repeating x values. So no repeats in x. We could have repeats in y, that's fine, happens all the time, but when we have a function, there are no repeats in x. So f of x is going to replace y in y equals mx plus b. We're going to say that could also be f of x equals mx plus b. And that tells us, without us having to think about it, that this is a function. Y is just the output, but f of x tells us it's a function right from the beginning. So when we have this, f of x is equal to 2x plus 4, we can tell it's a function because it says f of x. And actually, any linear relationship that has this mx plus b, as long as m is defined, meaning that it's a number, then we have a function. So if we were to look at this function here, 2x plus 4, well, this graph on the right shows us f of x equals 2x plus 4. And how does it show us that? Well, on the y-axis, we have 4. That's our y-intercept. Our graph goes through the y-axis at 4. Then we see the 2. That means that every time we increase by 2 in y, we are increasing by 1 in x. And we see that pattern repeat itself over and over and over again. And that's what makes something linear. It's that constant repetition. It's over and over and over again. Increase by 2, increase by 2. So we want to determine functions from coordinates. Let's say we don't have a graph. Well, if we want to map something, we would call this, on the right side here, we would call it a mapping diagram. And let's look at this one on the right side first. So we have our domain of 1, 2, and 3, meaning our inputs could be 1, 2, or 3. And our outputs, our range, well, those could be 5 or 7. So 1 goes to 5. That would give us the coordinate point 1, 5. 2 goes to 7. And 3 goes to 7. Now, this is a function. Why is it a function? Because none of our x values repeat. We have a consistent output for each input. When we input 1, we output 5. We input 2, we output 7. We input 3, we output 7. Now notice that these 7s repeat, but that is okay. Why is that okay? Because it's not the x value repeating, And so it is still reliable. You give me a 2, I give you a 7 every time. If we look at the one on the left, it's not as simple. So we're going to make our mapping diagram. We're going to say this is 2, 1. Well, the 2 actually repeats, so we're not going to put it again. 0, 1 repeats, and 3. So we can see already there's a problem here because the x values repeat. But we want to finish the diagram to show that that really is true. So let's put our y values here. And remember, x, input, domain, they all mean the same thing. So our outputs here would be -6, 4, and 4 repeats, 0, -6 repeats, and 0 repeats. So actually we only have 3 numbers in our outputs. So let's map these. 2 to -6, 1 to 4. So far, so good. 2 to 4. Well, that's where we run into a problem because 2 can't give us -6 sometimes and then give us +4 other times. So that's not going to work for us. This is already not a function. Let's finish the diagram. 0 to 0, 1 to -6. Well, that's a problem because 1 already gave us +4, so that doesn't work for us. And 3 to 0. Now, it's okay that 0 maps to 0 and 3 maps to 0 because 0 and 3 are 2 different inputs. They can have the same output, but you can't have 2 different outputs for 1 input. Here are other examples of this. 10 goes to 15, okay. 20 to 45, 30 to 25, 40 to 35. None of those inputs repeat, so this is a function. We look at the one down here, we see input of 2 gives us 20, and input of 2 also could give us 40, so not a function. And again, that's because our x values repeat. All right, other vocabulary words we want to use here are proportional and non-proportional. When we talk about proportional, we're talking about a graph that goes through the origin and is linear. When we talk about non-proportional, well, that means that it goes through anywhere except the origin. However, it's also linear. Both of these are linear, and that's extremely important to remember that when we use these words, they're only referring to linear functions. There are functions that don't make lines, they're not linear, but we wouldn't use these words to talk about them. Okay, so let's look at this graph on the left here. We want to find out, well, what is the function for this graph? What is the equation we would use? First, we're going to look at the y-axis. We're going to look at this point here, and we see that that is 5, 6, 7, 8. So b equals 8. Then we look at our slope. Well, we can tell that it's a negative slope because it's decreasing. So that's good to know. Then we want to look, well, our changes in y versus our changes in x. So if we start at 8, the next time we see it very neatly cross one of these lines on the graph is here. No, stop clicking. It's here. So we go down 3, 1, 2, 3, and then we go over 1. And then we can see that pattern repeating. 1, 2, 3, over 1, 1, 2, 3, over 1, 1, 2, 3, over 1. So we know that our slope is going to be -3 divided by +1, which just simplifies to -3. So our equation for this would be f of x is equal to -3x plus 8. This is our m, and this is our b. If we look at the graph over here, we see that the b value is 0. Well, that tells us right away that this is proportional. The b value is 0, so we know, well, it makes a line and it goes through 0, it is proportional. But what is the function for this? Well, we're going to look for the changes in y, and we're going to divide them by the changes in x. So we're going to say that we go up 1 and over 3. So every time we increase by 1 in the y, we're increasing by 3 in the x, so our slope is 1 over 3. Since our y-intercept is 0, we could say that our equation is y equals 1/3 x plus 0, which is really just y equals 1/3 x. And of course, we could write this instead as f of x equals 1/3 x. They mean the same thing because it's a function. All right, let's look at 2 more examples. Rise over run. So sometimes we'll refer to this as rise over run. It's the changes of the outputs divided by the changes of the inputs. And of course, outputs are y and inputs are x. So if we rise 2 and run 3, well, rise over run is a fraction. So we're going to have 2 over 3. That's our slope. We see that it goes through the origin. So the equation for this would be y equals 2/3 x plus 0. And we don't need to write plus 0. So we could just say f of x is equal to 2/3 x, or y equals 2/3 x. Now we look at the graph on the right side, and we see that it goes through 5. So we know that b is equal to 5. Then we see that every time we go down 2, we're going right 3. Down 2, right 3, and if this were to continue, down 2, right 3, and that creates our line, that creates our linear relationship. So if we go down 2 and right 3, well, right is always positive, so we know that the change in y is -2 and the change in x is +3, so our finished equation will be y is equal to -2/3x plus 5. We're decreasing by 2, increasing by 3, and we started at 5. All right, this summarizes what we've just looked at. If you want to copy this down, or if you already know this, then here's a refresher. So our slope here, rise over run, the same as change in y over change in x, which we know as this formula, y2 minus y1 equals x2 minus x1. Oh, sorry, over x2 minus x1. And so what we're really doing here is dividing the change in y by the change in x. All right, that's our video for today. Please make sure that you're doing the homework, and I will see you guys tomorrow.